more things I wanted to say about these Lie algebras, and then we move back to current algebras. Okay. We already discussed the computation of Casimirs in Lie algebras. Just want to give you a formula for the Casimir in terms of the dual Coxeter number. Perhaps we talked about it, but I can't remember, but I'll just remind you again. So you remember how we computed the Casimir, right? We acted with JA on the highest weight state. Okay, now JA is HH plus E alpha, E minus alpha plus E minus alpha, E alpha. The lowering operator kills, whatever, the raising operator kills, the lowering operator does not, but then you take commutator through, and you just get this, you just get what you get from the commutator of H with A. Okay, so we went through this process in the, in some class, and we found that the Casimir operator, let's call it Q, is equal to, was given by this formula, which was lambda and lambda plus 2 rho. And just to remind you, where did this rho come from? It came because we were doing this E alpha, E minus alpha over all alpha. So there was a lambda inner product alpha and sum over alphas. And that sum over alpha for all positive roots is rho. Twice rho. Okay. Okay. Yeah. So this formula we at some point seen. Now, lambda is the highest weight of. So we were acting with this Casimir operator on the highest weight state in the representation. Okay, excellent. So now I just want to process this formula a little bit more. And this processing goes as follows. Last time we derived this, we couldn't process it further because we didn't know the second expression for rho. But now we do. In the last class, we showed that rho was equal to sum over I over all the fundamental weights. Yeah, so sum over fundamental weights with multiplicity 1. Okay? And so if we take this, so let's do the following. Let's take lambda. Okay, let's take lambda and so this is of course just in general, this is the formula. That's right. So suppose now we are in the adjoint representation. Okay, in that case, lambda is the highest weight for the adjoint representation. But you remember that highest weight, we'd given a name, it was called this theta. And you remember that the expansion of theta, okay, that the expansion of theta in terms of these AIVs, do you remember what these AIVs were? These AIVs were, alpha i's, but normalized such that this was, mod I square. Okay. So in terms of the simple roots, but with this normalization, okay, those were the AIVs, and the coefficients of that we'd call some mark or co-mark or something like that. What? Alpha, yes, alpha. Yeah, and this is AIV. These AIV has some name. The expansion of any weight in a basis which is this alpha IV, the coefficients of that AIV. And you remember that this AIV, that sum over all I of this AIV, the coefficients, was equal to the dual Coxeter number minus 1. Okay, this thing we call G minus 1. That was our definition of this dual Coxeter number. Okay, so what we're going to do now, so this was just a reminder. Now what we're going to do is to plug this guy into that formula. Okay, so lambda is sum over I, AIV alpha IV. Then we've got lambda is sum over I, AIV alpha IV plus 2 rho. but rho itself was sum over j omega j. Okay, and we wanted a factor of 2, so we got a factor of 2. Okay, now we're going to so let's do these one by one. This guy with this guy. Okay, remember alpha I with alpha alpha. First, let's do this. This is the easier one. Let's do this guy with this guy. Okay, this guy with this guy is easy because alpha and omega click. You know, it's delta ij. Okay, so what we get from here is simply 2 times sum over aiv. Right, because each of these guys click with one of those guys. Okay, and so this quantity was equal to 2 into g minus 1. Okay, and now what about this guy with this guy? Well, this guy was just a root. It was just one of the, it's one of the highest, it's one of the long roots. This is just theta with theta. So in our conventions, it's 2. Yeah, so it would be complicated if we did it this way, but just think of it as a basic object. So it's 2 plus this. Okay, so the sum of these two is 2 plus 2 into g minus 1, which is equal to 2g. Okay, so this you can think of as another definition of the dual Coxeter number. The one that is maybe less nice for the mathematicians, but more practical, in the sense that, and this is how it will enter physics. I mean, in most cases, in most formulas, you don't get these AIVs and so on, but you do get Casimirs in the adjoint representation. Okay, so so the dual Coxeter number you can think of. You can think of this dual Coxeter number as being defined as follows. It's TA in adjoint is equal to 2g. Okay. Now this TA we can make more practical, right? Exactly. So this is so remember we define structure constants through this formula, where TB is equal to F ABC TC. Okay. Now we think the adjoint representation, you can think of the matrix as, you know, A as a matrix, as a Witch generator index, and B and C as matrix indices. Okay, so let's think of it that way. So then this quantity is FABC, FACE, right? Because these are the Witch. These are these indices, they're summed, and these are the matrix indices. So this has to be identity, that's the first thing. But identity was delta BC. And then it's identity times this number, so 2g. Okay, so if you want, you can think of this dual Coxeter number as being defined through this equation. It's equivalent to the other definition. And it's the thing that will enter in physical calculations. Okay, clear? Excellent. One. It will appear in the central charge, exactly. Yeah. What? BE, yes, B. This was F. You may not. E. Oh, thank you. Thank you. Yes, B. Yes, exactly. Okay. Now one more notational convention. Okay. One more notational convention that will be useful, for instance, when computing weights of primaries. Okay. You see, we have defined. Let me get the definition. in the convention which highest weights always have length 2. Highest roots, longest roots always have length 2. That's always a convention I use. Sometimes, sometimes you want to write things in a convention-independent way, in which case you look to see where the killing form has appeared in your equations. And then, if you get a lower killing form, you multiply your formula by 2 and then divide by the length square of the highest root. So that it becomes independent of how you've normalized. Okay, but okay. So, but always using conventions in which highest root has length 2. This is, as we've just seen, every time you've got a length of something, you can go between that normalized convention. Okay, we can define the following. Suppose I've got a representation R for the group, and I've got TA as generators in the representation. Okay. Now, suppose I compute trace of TATA in the representation R. The representation R means that we've got some matrices. Okay, some dimensional matrices. We compute the trace of this object. Question, what is this? What does this equal? Well, that's clear. That's clear because we had a formula for what TATA was. In representation R, it was that formula up there. Let's get it back. It was lambda times lambda plus 2 rho. That was TATA. And then we take trace, because as identity, you get the dimensionality of the representation R. Okay? Fine. Now, people make the following definition. Okay? This quantity, and then, sorry. I'm sorry. Yeah, okay, this is true. Now, people do the following. They ask, suppose you have trace in representation R of TATB. Not A and B, not AA summed. This guy was sum over A. This is just trace and representation R of TATB. A and B are different. Well, this is a group invariant pairing of generators, and we know that's unique in this group up to overall normalization. Okay, so this guy here, killing form, so we call that delta. Yeah, this guy here is delta AB times some number. And let's define this number to be 2 times XR. Okay. This XR is called the something of the representation. The index, I think they call it. Yeah, this is called the index of the representation. Okay? It depends on the representation we choose. Now let's find a formula for the index of the representation. Okay. What we do here is just sum over, set A equals B and sum over all A. Okay? Then that quantity gives us this quantity, but it also gives us 2XR times dimension of the group. Is equal to lambda plus 2 rho dimension of the representation. Right? And therefore we find that XR is equal to this lambda plus 2 rho times dimension of representation divided by twice dimension of group. Let me check this formula. Yeah, dimension representation divided by twice dimension of the group. Okay? And finally, we can ask what is the index? What is the index of the adjoint representation? Now, in the adjoint representation, we've already seen that this guy is 2G. Then we've got this then we've got this dimension of representation by dimension of group. But in the adjoint representation, the group, the generators are the representation. So the dimension of representation is the dimension of the group. So this just cancels. So we get 2G by 2. So this is equal to G. Simple. X adjoint is equal to G. Okay? So the index of this representation is something that is, of course, easy to, it's an abstract characterization somehow of size squares of representations. Okay? And just for fun, so now if you want if you want to work in a completely basis independent way, you can think of, you can think of the index of the representation by G as being trace TATA, as being Casimir times dimension in representation divided by the same thing in adjoint. Okay? Fine. I think that's sufficient for now. As an exercise, I encourage you guys to work these things out for SU2, just to see what they are. Yeah, and okay. I think that's all I wanted to say about normalizations and these names. Okay.
Can you tell me one thing? This how to take the define the trace in basis independent way?
What do you mean basis independent way?
I mean, sorry, representation independent.
A trace depends on representation.
I see. So is normalizing by something?
You see, that's the point of this index here. Okay, that the trace in different representations is a different object. Once you've chosen, you see, these normalizations are all very confusing. So you should remember to distinguish two things. First, you have, within your Lie algebra, viewed as an abstract space, you have to choose a normalization for operators. What you call H, what you call E. Okay? Now, we chose that by defining a particular, in order to do that, we chose that by saying something about what their lengths were. We said H was normalized to 1, E was normalized to, this 2 by mod alpha squared. But then you needed to know what the norm was in order to make that definition. We chose a particular definition. You remember we chose this killing form to be trace and adjoint representation divided by 2G.
2G, right.
Okay, so we chose that definition. With that definition, we chose our generators.
Right.
These are now in the abstract linear Lie algebra space, we've chosen them. Now we take the same generators. Don't renormalize anymore. We take the same objects, okay, and view them in a particular representation. Now we take trace of TATB. We'll still get delta AB, but with a different number. We've seen what we get it with in the adjoint. It's basically this 2G, right? Okay, but we get this with a different coefficient, and the ratio of these two is this index. Okay, so the proportionality was determined just by invariance. There was only one invariant form, group invariant pairing. Okay, but the number was not determined by anything and changes representation by representation. Okay, is this clear? Okay, great. Okay. Now there is one last thing I want to tell you about Lie algebras. One last thing that we want to discuss about Lie algebras. We will come back to Lie algebras as when we try to understand modular invariance, Berlin formula, things like that. We will come back to Lie algebras. But it's just getting too boring to keep on about Lie algebras. So we'll just move on to current algebra soon, and then come back when needed. Okay, but there's one last thing I wanted to tell you about, which is very useful to know. And I'm not going to try to attempt a derivation of it. I'm just going to try to give you the result. The result is this, that there is an abstract formula that computes the character of any representation in any group. So I have to first tell you what is a character. So what's okay. So suppose I give you a representation. The thing about that representation you want to know is what are the weights that appear in the representation and with what multiplicity. Okay? This thing completely characterizes the representation. Okay? Remember what weights were? They were the eigenvalues under the HIs. Remember, all weights lie in the weight lattice. Okay? So there's a discrete infinite number of possibilities, and I have to tell you for each of these possibilities which ones appear and with what multiplicity.
And the dimension of the weight is the rank of the group, the number of.
Exactly. The dimensionality of the lattice is the number of Cartans. Okay?
And the number of vectors are the number of the generators of the group, the number of the weight vectors.
Number of weight vectors. What do you mean by that?
Fundamental weights will be number of.
Yeah, the generators of the lattice are this Cartan. But the number of weight vectors in any representation depends on the representation. Right? It can go from 0 for the identity, or maybe 1 you'll call it, the origin, to infinity. Bigger and bigger representations. Right? In SU2 and the representation J will have 2J plus 1 weight vectors. Okay? Great. So that's what we want to know. Now, this might remind you of a problem in physics. Replace eigenvalues under, actually, suppose we were doing hydrogen atom. We might want to know about the states of the hydrogen atom. We want to know which energies appear, which angular momenta appear, with what multiplicities. Okay? This is a very common kind of question we ask in physics. We choose our generators, we choose them to diagonalize them, and then we want to know about the spectrum in terms of values for these diagonal generators. Okay? So this is that kind of question. But we also know in physics that is often more convenient. Okay? Giving the states and which energies and which charges appear is like a microcanonical point of view, specifying all the states. But there is another quantity that very efficiently encodes this information, which is the partition function. Okay? So, for instance, suppose we were just looking at things as a function of energy. In quantum mechanics, we could, of course, specify all the states. But it's some unwieldy object. It's a list. Okay? That information is very nicely encapsulated in trace e to the power minus beta h. Okay? And once you know this object, how do you go back to what you want? Well, you just take the coefficient of e to the power minus beta e naught, and that's always an integer. And that integer gives you the number of states with energy E naught. Okay? So what did we do here? We introduced some object, this e to the power minus beta, which we'll sometimes call q to the power h. Okay? This q was something formal, but you imagine it as being less than 1. In Lie algebras, it will be complete because it's finite. Less than 1, more than 1 will not matter. But once again, current algebras will matter. Right? So, but imagine it as being less than 1. expand this thing in an expansion in this Q, higher and higher powers, and isolate coefficients of this power. That gives you the full spectrum of the theory, right? This is something we're extremely familiar with. Okay? Now we can try to do the same thing for Lie algebra representations. Okay? We can try to do the same thing for Lie algebra representations. I will first say it formally and then say it less formally. Okay? So what we do is for every H vector, every Hi, we introduce a Qi. Okay? And then we do product over I, Qi to the pi Hi. Product over I, Qi to the power Hi. Okay? And then, sum over all. Or if you want to think of this, this is like the trace over the representation. Okay, so you've got one state which has some, so you'll have Q1 to the power 2, Q2 to the power 7, Q3 to the power 4. The coefficient of that gives you the state, the number of states with weights 2, 7, 4. Okay? Now, this thing looks like a slightly formal object, but there is another way of thinking of it, which is this. You see, these HIs were infinitesimal with the deviations from 1 of a group element. So when we exponentiate HIs, and if we want to think of these guys as Hermitian operators, we'll exponentiate them with an I. Okay, when we exponentiate HIs, so let's write this Qi, suppose we do Qi is equal to e to the power I theta I. Okay, so we exponentiate this e to the power I theta I Hi, product over I. And this product is, there's no subtlety here because these HIs are mutually commuting. You don't have to worry about ordering and things like that. When we exponentiate that, what are we getting? What we're getting is the most general diagonal group element. Okay. Maximal torus, doubtless. Okay. So, yeah, exactly. The maximal torus because, he's saying torus because, these thetas are periodic things. So, it's a maximal torus, right. So, we're getting the most general diagonal group element. And then we're taking the most general diagonal group element with these, how much you're putting behind these HIs viewed as the chemical potentials. With or without an I, it's a formal element. I mean, from that point of view, it was a formal thing. Here, it's not formal, it's a group element. And we take the trace. Right? So, what we're saying is that this guy is trace G, where G so far was a diagonal group element. Okay? However, we can forget about this diagonal group element business. Because you see, in Lie algebra, every element of the Lie algebra was similarity equivalent to a diagonal guy, namely a Cartan element. And the group analog of that is that every element of the gauge group, I mean not the gauge group, every element of the group is similarity equivalent to some diagonal group element. But under similarity transformations, trace doesn't change. So you see, trace is not labeled by group elements, but by equivalence classes.
Class functions.
Yes, class functions. Fantastic. Okay, two group elements have the same trace if they're similarity equivalent.
They're related by some similarity.
Similarity transformation. And so you can think of group elements as being parametrized by their eigenvalues. Okay? And these, you diagonalize them, there's some wild reflection symmetry ambiguity. Because you can take these different group elements and switch them around. Which eigenvalues, like for instance in let's say SUN, whether it's this way or that way. Switching various eigenvalues around. It's clearest in UN actually. Switch all the eigen. Yep.
So every group element in this Lie algebra will have a distinct set of eigenvalues, right?
Not, I mean, if you're very serious about the word distinct, not necessarily. Right? Because two things that are equivalent, similarity equivalent will have the same eigenvalues. So eigenvalue is a characterization of the group element, but it's a many-to-one characterization of the group element. Many different group elements have the same eigenvalues.
Okay, because they're
Because you take one group element, do, so let's call it G, then do G1, G, G1 inverse.
let's say you fix some basis, then you'll have just a specific distinct eigenvalue, right?
Distinct from what? Do you mean well-defined eigenvalues?
As in, when we were doing this simple roots and all, we were specifying some basis, right?
Yes.
And then all the eigenvalues for each distinct roots were distinct.
Yeah.
In
Yeah.
that sense, it will.
Okay, good point, good point. Yeah, so in this case, I mean, imagine that we had a matrix group or a representation of the matrix group, or some matrix representation of the group. What we will get is a diagonal object. Now, this diagonal object in a general group, let's say in SUN, let's take SUN as an example. It's diagonal, but it's not the most general diagonal element, because product of eigenvalues will be 1. Okay, now this basis business is about how you're going to choose a basis in this, for these n different eigenvalues. There's an n minus 1 distinct basis elements, right? Because of this product. That's where the basis dependence comes in. Okay, but viewed as just a matrix, it will have something. So what we will have in general in a general group is relations, that they will not be the most general diagonal element, like we just saw. Okay, and then you choose a basis, and with that basis you pick out the eigenvalues, the coefficients for particular HIs. That now is your definition of what your HIs are. It's often nicest to think in terms of the weight lattice. These weights, the weights are some element of that abstract weight lattice. And then you can choose different bases for that weight lattice. Okay? But maybe that's too abstract, whatever. Okay, great. So this character now has another manifestation. Okay? It's just a trace of the group element. Okay. And though we're not going to try to see proofs of most things I'm saying here, this way of thinking is often very useful. Why is it useful, by the way? It's useful because characters have an orthogonality relationship. Okay? That if you have trace in R1 of G and trace in R2 of G, same G, and then you integrate over the Haar measure. There is not even discussed it, but on the group manifold there is a unique group invariant measure that's both left and right invariant under group multiplication. It's called Haar measure. For SUN, for instance, many of us are familiar with the form of that measure, right? Unwu more than most people. I mean, this sine kind of Van der Monde, right? So, okay, so there is this. The result is that this thing is proportional to delta R1, R2. And if you choose these characters to be normalized appropriately, that coefficient can be made 1. Okay? So thinking of this character in terms of groups has great benefit. It's not just cosmetics. Because once you think of it as in terms of group elements, it is natural then to integrate over the group. And from that you get orthogonality. By the way, okay, fine, forget it. Again, if there's any more detail you'd like to know about anything particular, please ask. And we will need some of these as we go on. We may give more detail as we go on. Right? Okay. So this character of representations associated with a given group is a very useful thing. Okay? There are two things about characters that I wanted to briefly discuss. Okay. The first thing is a very explicit formula for these characters, which I'll give you an abstract version of. And then for SUN, I'll make it concrete. What? While character formula. Yeah, this is one of the most, a lot of what, well, I don't know how you guys are, but there are some things that you do like physics, right? Which are sort of easy to do. And then there are these mathematicians, I don't know how they think. Maybe they think like physicists, but they hide it. I'm not sure. But sometimes they come up with these formulas that you feel, how did they do that? It's not so hard. You just have to figure out all the degeneracies of all the weights, etc. It's not so hard, but somehow, anyway. So this is one of those formulas where you feel, wow, this is not what I would have come up with. Yeah. Okay. And I'll tell you the formula. The formula goes as follows. Okay, first I'll write down a formula and then I'll tell you what every term means. Okay, where is this formula? Chi in representation R is equal to sum over the while group. This little w is an element of the while group. You remember the while group, right? These SU2 reflections. Okay. Little w is an element of the while group, and then I'll write various things I have to tell you what each term means. Epsilon w divided by e to the power w of lambda plus sum over w Okay, let me tell you what each of these things mean. And first, what is epsilon w? You remember that every element in the while group could be constructed out of products of reflections associated with simple roots. Fundamental reflections. Fundamental, I called it. Okay, yeah, fine. So the simple roots, you act with the while reflection associated with simple root maybe many times. And then all the simple roots, you get all while reflections. Okay? Now, there is this question of, in order to get a particular while group element, do you need to act with an odd or even number of reflections with simple roots? Okay, it takes some showing that all this doesn't depend on your basis and so on, but presumably one can show it. I've never gone through it myself. Okay, and this epsilon of w is 1 if your group element is even and minus 1 if it's odd. So for instance, in some contexts, the while group is sometimes the permutation group. In that case, let's say you have permutation of n elements as you would in SUN. Okay, in that case, it's just whether every permutation element is odd or even. And that is, of course, a very familiar notion, right? How many transpositions do you have to do starting from identity to reach a particular permutation element? And there are many different ways to get to any group element, any permutation element with transpositions. But the question of whether it's an odd or an even numbers, however you get it, is always the same. This, I think, many of us are familiar with. It's like that kind of notion. That's what epsilon of w is. Okay, is this clear? Please.
So let's say this is a previous question. Maybe.
Yeah, go on.
Starting from some simple root, you can't cover all the roots, right, just from reflection.
By reflecting, oh, you can. All. In fact, don't you, yeah. By reflecting with, okay, what is the question again?
Yeah, starting from a simple root.
Yes. Can you go from one particular simple root via while reflection to all roots? So now certainly it's not true for an arbitrary. So while reflections also act on weights.
Yes.
Okay. What you can do is take all weights and put it into a fundamental kind of chamber. Okay. So weights, maybe for roots there's something special. Let me answer for weights, where I know. Weights in general occur in orbits of the Weil group. Any two weights that can be mapped to one another by some element of the Weil group. Let's say they're equivalent. Now, what people do is this. There is a theorem which says that by acting with the Weil group, and maybe it's an obvious one, by acting with the Weil group, you can put every weight into a fundamental chamber defined by the criterion that the inner product of the weight with the fundamental weights.
Any weight with a fundamental.
No, probably with the fundamental roots, probably with the alpha IV. Okay, inner product of the weight with these alpha IVs is positive. Okay, so for SU2, that would be all the positive roots, all the positive. Yeah. Okay. Now already we can answer for SU2. Yeah. So the answer is no. It's not always positive or it's non-negative. So in SU2, for instance, the three roots. No. So in SU2 you can. Right. So in SU2, the two roots are +1 and -1, and the Weil reflection maps the two. Maybe for roots it's always possible. I'm not sure. Let me see if the book says something about this. For weights in general, there are many weights in the fundamental chamber. So those are not Weil equivalent. But for roots, let me check. There may be a statement. So I think that what is probably true is that the action of the Weil group on all simple roots gives all roots. I think that is probably true. The action of the Weil group on all simple roots, positive simple roots, gives all roots. Yeah. For SU3, I once checked. I know this is true. SU2, we've just seen it. I think that's the statement. So not that every root is Weil equivalent, but every root is equivalent to a simple root under Weil reflections. Okay. Excellent. Okay, other questions? Great. Fine. So first I still have to continue telling you what this formula means. Epsilon we've understood. What are these objects? Well, you could have chosen any roots as simple roots. Exactly. Right. Any collection of roots.
Simple root by Weil.
Yeah, right. You could move to some other chamber. Yeah, exactly.
Why would that not be true then for the weights also?
Why? Because
Equivalent statement must also exist for the
there is an equivalent statement which says that people give it a name. There are things called, they call them dominant weights. All weights can be obtained by weights in the fundamental chamber by Weil reflections. Okay? And whatever is in the fundamental chamber, you call dominant weights. But the number of dominant weights depends on the representation. So in fact, this Weil character formula, for instance, is obtained first by looking carefully at these dominant weights and then reflecting. That's why this Weil group comes about. right? Because you first characterize this fundamental chamber, and then you look at all the reflections. Okay. Yeah, so there is an equivalent statement, but it's not a, it's just a name, right? Whereas in the case of the adjoint representation, we know what the dominant weights. Okay, great. Excellent. Okay, excellent. So, what are these objects? Well, you can think of this in many ways. This object is the following. You can think of this abstractly as the exponential of an element of the weight lattice. That exponential just tells you about an element in the weight lattice, but it's an exponential because we have product of two elements in the weight lattice. It adds up there. Okay? So, but of course you can think of it less abstractly in the following way. Okay? This guy was just, what do we call them? Rhos? Rho-I, H-I's. Okay? With coefficients being the coefficient of this weight vector in the HI basis. Okay, let's say for instance we choose HI to be the dominant weights. The basis of dominant weights. Okay? Then you take away a lattice vector, you expand it in dominant weights. It's got some integer coefficients. And that integer appears with the Rho-I. Is this clear?
So
Okay.
this is a vector exponential.
A vector exponentiation of you can either think of it formally, or you can think of it as actually chemical potentials multiplying actual these elements and taking a trace. So you can think of it as trace of this guy, but where this vector tells you with what power you get these HIs. Is this clear? Is this clear? What? Yeah. What this means. Suppose I've got a vector here. This vector is a vector in the weight lattice. Okay? So I take that vector in the weight lattice and I, if you want, expand it out in a basis of HIs. For instance, I can take the dominant weights as my basis. So this vector in this basis has n1, n2 up to nr. Okay? Then this guy would be rho1 to the power n1, rho2 to the power, then forget the trace, rho1 to the power n1, rho2 to the power n2, rho n to the power n. That's what that means. Okay, just chemical potentials. The way they like to write it this way because it's independent of which basis you use. Think of it abstractly like on the weight lattice. Okay, so it's just keeping track of lattice vector, and there's an integer behind exponentially that lattice. You write it as exponential because you want to be able to take products. And the rule is that if you take one exponential of one lattice vector times exponential of another lattice vector, then an exponential of the sum of the lattice vector. These are all abelian, right? Because all the h's commute. Please.
Is there some way of this looks like something when you are calculating path integral, let's say, you have this insertion of e to the power omega lambda, and then you take average.
Omega lambda. Omega. This W, by the way, is a while element. Huh? So this was some weight vector. Then you act with a while vector, you get another weight vector. Okay. You have to do the same in the denominator. Okay. So this is a sum over discrete number of weight vectors. Now, just one more minute before we come back to your question if it's still there. This looks like a very strange object because of the denominator. What the hell does it mean when you've got this denominator with these exponentials of lattice vectors? But what one can show is for finite groups, and something similar will be true for other situations, is that the numerator always has a factor that cancels the denominator. So this quantity is actually a polynomial. It's a finite number, it's got a finite number of weight vectors. Okay, so this is a way of writing it. But there is, when you actually work it out, we would get a finite. Let's. Let us, just to see how it's working, let us work it out for SU2. Okay. SU2, what is the character? Let's first independently calculate it and check that it's giving the same thing on the top. Okay. For SU2, suppose we've got spin j. We've got rho to the power jz. Okay, that is our operator, rho to the power jz. So what would we have? We'd have rho to the power minus j plus rho to the power minus j minus 1 plus rho to the power j. Okay, this is just what it is. Now this is a geometric series. Okay, this is a geometric series. So we can sum it up. So let's do that. Let's write this as 1 over rho to the power j into 1 plus rho to the power 2j. Okay. This is equal to 1 over rho to the power j into now 1 minus rho to the power 2j plus 1 divided by 1 minus rho. Okay. Now let's multiply this rho to the power j here. So we get rho to the power minus j minus rho to the power j plus 1 divided by 1 minus rho. And now we'll take this 1, let's write this as e to the rho to the power, which is equal to rho to the power minus j minus half, plus half minus rho to the power j plus half over rho to the power minus half minus rho to the power half. And it's most usual to write it flipping both numerator and denominator. So we get rho to the power j plus half minus rho to the power minus j plus half divided by rho to the power half minus rho to the power minus half. Okay. Now, how is this related? How is this related to this Wilde reflection formula? Okay, the denominator was this quantity. The denominator was this quantity, you see, because what was rho? It was the sum of all positive roots. Positive roots in this case is just 1, with weight 1, but rho was half of sum over all positive roots. So that rho had weight half. Right, I mean in units in which we're working half integer jz. In dominant weight it would be 1. Let's do it the way we're familiar.
Yeah, so the denominator has to be dominant.
What? W rho. Thank you. W rho. Yeah. Okay. So rho had weight half. So the denominator here, therefore, was 1 over rho to the half. That was the first term. Minus the Wilde reflection. Wilde reflection just flips jz for minus rho to the power minus half. Okay. What about the numerator? Well, the numerator, lambda had weight j, but rho has weight half. So it's rho plus half, and then rho plus Wilde reflected. So j plus half, and then minus of j plus half. Why the minus sign in both cases? Because epsilon w was 1, because you had to do one reflection. So it was epsilon w was minus.
While group is in this case Z2,
Z2, exactly. Okay? So you see how it's working in the case of SU2. You got this strange looking denominator. You get the strange looking numerator, but you can factor them. And that cancels the denominator. And you're left off with a polynomial. Okay, is this clear? Okay, so right to end this part, just to end this part, let us now, I'm going to give you one processing of this answer for SUN. Okay, that is in the case of SUN, this thing can be written much more nicely. And it's a beautiful formula, and one that's very useful. So I just want you to see it.
Something that you written in your paper.
Yeah, the determinant formula. Yeah. Okay. Now in SUN, you remember from the last class that we had two different ways of characterizing representations. First, by number of rows, the number of boxes in the ith row, we called that Li. And then there was the number of columns of length I, which we called lambda I. This is the dominant weight characterization of SUN representations. This is often more useful for many formulae. The number of boxes in the ith row is often a more useful, as you will see, it often appears in actual formulae. Okay. Is this clear? With what I'm talking about clear? You remember this, right? Okay, excellent. So now what you do is the following. You look at the quantity, this. Okay, first I'm going to define n chemical potentials, Q1 to Qn, such that Q1 is the chemical potential for the fugacity. Fugacity is the right word, because each of the chemical potential. Okay, is the fugacity for this matrix, the diagonal matrix with just one in there. Q2 is the one with this guy, Q3, and so on. So there are n of these. Okay? Now the fact that all that actually the matrix was traceless tells us that we've done some overkill, right? That we didn't need all these chemical potentials. For instance, if we knew the power of Q1, Q2, Q3 up to Qn minus 1, we could figure out the power of Qn. So at the end, if you want, you could set one of these chemical potentials to 1. But there's no harm in doing this. Do you understand? Okay? So another way of saying it is that if we take all Q's and phase them by the same quantity, Q goes to e to the power I alpha, the answer will be invariant under this. Okay? So in that sense, this is a familiar kind of trick, right? You write a redundant description and then impose a gauge invariance. That chemical potential shifted in a certain way give you the same answer. But because this deals with the actual eigenvalues of the matrix, it's much nicer than choosing some funny basis. Okay? Okay, so I'm going to work with these fugacities, Q1 to Qn. First, is that clear? Now, I've got some representation labeled by Li's, the number of rows of the ith column. I want to find the character for that using these fugacities. What is it? It's a beautiful formula. Okay, and the formula goes as follows. Consider the matrix Mij equals Qj to the power m plus Li minus 1 and minus 1, I think. minus I. Okay, so the jth element, let's row column won't matter, but let's say that we say the jth column only has qj's. Okay, and how many powers it comes to depends on the number of elements in the ith row, number of boxes in the ith row, according to this formula. So this is some matrix. Now compute determinant of M and divide that by the same thing with all L's equals 0. So let's say that we could define M naught ij to be equal to q to the power n minus I. Q to the power n minus I. Okay? This det M by det M naught, det M by det M naught is the formula for the character of the representation, labeled by Li. Is the claim clear?
Yes, the claim is clear. What will this M naught represent, like in terms of determinant of M naught? What will it?
It will. Let's work it out for SU2. Okay, let's work it out for SU2, then we'll see what's going on. We'll work it out in this language, but for SU2, of course, the two chemical potentials are just inverses of each other. Because if you've got weight here, you've got minus the weight. Right. So first, let's work it out in this language, and then we'll let's work it out for SU2. It will give you the denominator of that thing, but let's see. Okay. So let's work it out for SU2. Now, how do we put SU2 in Young tabular notation? Exactly. The number of the fundamental, namely the two-dimensional representation of SU2 is one box. The spin 1 is two boxes, and so on, because you can. This row is symmetrizing, and you know that you get spin j by symmetrizing 2j copies of spin half. Okay, so what was L? Let's say, so what was L1? That was equal to 2j. And L2 is equal to, of course, 0. There's no boxes in the second row. Okay, now let's work out this quantity. What is, so I'm going to write down the matrix. So let's say the first one is, in the first column, let's say I have Q1s, and the second column I have Q2s. And now I have to know what to put, what powers to put here. So as you were saying, let's do for I equals 1. Okay, so we get 2 plus 2j minus 1. Okay, 2 plus 2j minus 1. So that's equal to 2j plus 1. Q1 to the power 2j plus 1, 2j plus 1. Okay, what about in the second row? In the second row, Li was 0, I was 2. So just 0. Okay, so this to the power 0. Okay, so I have to take the determinant of this divided by determinant of the same thing, but setting j equals 0. So Q1, Q2, 1, 1.
So there's another constant. Product of Qi is 1.
Yeah, that's why Q1 will be 1 by Q2.
1 is 1 by 2.
Because that would be one way of making it, if we wanted Q1 to the power something. Right. So this thing now will give us what? It's just Q1 to the power 2j plus 1 minus Q1 to the power 2j minus of 2j plus 1 divided by Q1 minus Q2. And now we set Q2 is 1 by Q1 because of this. If you, Q1 to Q, what? Q1 and Q2 up to the power plus, yeah. Q2 to the power, at the moment I've not set Q1 and Q2 equals, just Q1, Q2. Then we set Q2 equals 1 by Q1, okay? And you see we get the same formula except that our Q is identified with, with rho to the half. That's because that was working with j half integer, and this will be working with j some integer kind of thing. It's some relabeling some, yeah. But you see we get the same formula basically from this. Okay, so you see the role of that denominator determinant. It was to produce the denominator of the wild character form. And the numerator determinant produces the numerator of the wild character.
This explicitly works for SU.
This only works for SUN.
No other.
Maybe some, but it doesn't work for SON, for instance. There may be some modified version. Okay, I mean, related to the fact that the Young tableau representation, Young tableau labeling works for SUN. So even the data, what would the data be otherwise? Okay, excellent. Now, are we going to start? Okay, maybe I'll say one last thing about characters.
These polynomials are called Schur polynomials.
Okay, let me tell you about Schur polynomials. These are called character polynomials. Okay? Now, there is one other thing about characters that is often interesting. Let me say it in the context of SUN. Suppose I've got some character in representation R of a group element. Let's say we're looking at SUN. That's something. Okay? So I've got some character, oops, sorry. It's okay. Now, there is a particularly nice representation for SUN, namely the fundamental representation, n-dimensional representation. So, the character of the same character, let's call it a fundamental, of G is just trace G, where G is an n cross n matrix. Right? So, you take G as the n cross n SUN matrix, take its trace, that's the character, in the fundamental representation. Okay? The character in some other representation, some stranger object. Okay. Now, you see, because this guy has some weights in it, and every weight can be built out of products of weights of the fundamental representation. You see this from the Young tableau construction. You just take tensor products of fundamental representation, you get every representation. Okay? Every weight can be built out of weights of the fundamental representation. You may wonder, is it possible to do the following? Is it possible to write chi in an arbitrary representation as some polynomial? Polynomial because only finite, all representations finite number of weights. Some polynomial of chi in the fundamental representation. Or equivalently some polynomial of trace G, where I always mean trace G in the fundamental. Okay? It is possible. Always is possible. Okay? And the polynomial, and I'm not sure of the names, but let's call it Schur polynomial. I may be mauling the name, this may be some other name, but okay, I think it's Schur polynomial. The expression for the character in an arbitrary representation as a polynomial, okay? Oh, sorry, and this is actually polynomial of not just trace g, sometimes you need trace g to the n. N is any integer. So you can't always get it just by traces, but you can get it by trace of g to powers. Okay, right. So the expression of trace of something in an arbitrary representation in terms of traces in the fundamental representation is a very useful thing in many contexts. I'm not sure I'm getting the name right, but I'm going to call this the Schur polynomial.
It's trace g to the power n, not trace g to the whole power.
Yeah, since we have a polynomial, that will already be there. Let's work out an example to start with. Okay. Let's take the example of this representation. Okay. Now, I'm going to ask you what is character in this representation in terms of trace g. Now, if you think about it, you already know the answer. You know the answer because this is just Bose statistics. What we're looking at is the following problem. Let me imagine I've given you the one particle partition function. One particle is one box. I want you to find the two particle partition function, but not an arbitrary two particle partition function. Two particle partition function imposing Bose statistics, symmetry. Okay? And if I'm giving you the answer and you tell me if it's clear, this is trace of g square plus trace g, the whole thing square plus trace of g square divided by 2. Let me explain why this is the case. Okay, let me explain why this is the case. First, I'll explain it simply, then in a way that is nicer. The simpler explanation is simply this. Look, if we are not sophisticated, we account for symmetry by taking trace g times trace g and saying, okay, we've overcounted states with factor of 2, so we divide by 2. Okay? And that's good, except when both particles are in the same state. In the case that both particles are in the same state, we shouldn't have divided by 2. Because you got both particles in the same state in only one way. So you have to add in half of both particles being in the same state. But if both particles are in the same state, you have twice the energy of the one particle Hilbert space. Because the states are just the states of the one particle Hilbert space, but with double up energy. So this was the partition function pretending they were not identical. This was the naive dividing by 2. And then we have to account for the fact that we have cut down the states where both particles were in the same state by a factor of 2 when we shouldn't have. So we add trace g squared by 2. Is this clear?
Should you not subtract?
Oh, we would for fermions. You see? Yeah. Okay. So, you see, suppose we've got some Hilbert space. So the particles have energies EI. Energies are weights under SU n, right? But I'll say energy because we're more familiar. Okay? The Hilbert space is E1, E2. This is the Hilbert space, where E1 and E2 run over all values, except that we are looking at symmetric. So we only should count E1 and E2 not equal, but of course we should count E1, E1. So these two where they're not equal counted only once. E1, E2 is same as E2, E1. But E1, E1 is not same as anything else. It's just same as E1, E1.
But they were already counted, right? When E1 and E2 were equal.
Good. So suppose we counted. So now what we did here is count all states, ignoring the fact that we were supposed to impose that E1, E2 was E2, E1. So when we divide by 2, when E1 and E2 were different, that correctly accounts for, because we counted E1, E2, we counted E2, E1, and we divided by 2.
Different E1, E2.
When E1 and E2 were different. But now suppose E1 and E1 were the same. Then the correct thing, even with both statistics, is counting each state once. But here what we did is divide by 2. So we counted each state half times. That was wrong. We need to add half. And that's what this does. Shall I say it more clearly? It's fine? Say more clearly? Yeah, okay. So suppose we had e to the power minus beta h. What is the contribution from, okay, let's say it more clearly. I'll give you another derivation as well. But suppose we had e to the power minus beta, trace e to the power minus beta h. Okay, and let's suppose E runs over EI. Okay, what is the correct answer? The correct answer is sum over I not equal to j, let's say I less than j, I greater than j. So pairs, sum of pairs, let's call it. Pairs I, j, I not equal to j. Okay, trace e to the power minus beta ei plus ej plus sum over I equals j. So that's just I, e to the power minus 2 beta ei, because the two particles have the same energy. Okay. Now let's check what happens when we just compute trace. If we just compute trace square, that is sum over I, e to the power minus beta ei, the whole thing square. So that's this, sum over j, e to the power minus beta ej. Okay, if I take this and I divide by 2, as I've done in that putative formula, then what do I get? Here I had a term, every term which I was not equal to j appeared twice. So the division correctly produces this. But every term where I equals j, you get this e to the power minus beta I, but with an extra half. So this thing is equal to this plus half this. Do you see that? Okay? So we want to add half of this. How do we do it? Well, half of that is simply half of trace e to the power minus 2 beta j. Right? Because that's what this is. Clear? Okay? And so we conclude that trace
For 2 beta sum over this compensate, this is added by this.
exactly.
This half adds up and get.
Exactly. Okay. Now, what would we do if we had this representation? So we've concluded that this trace this of g is equal to half trace g the whole thing square plus trace of g square. Let's say by 2. We concluded this, right? Now, what about this guy? It's clear here we got that extra half, which with Fermi statistics we would not allow. You have to remove them. So this will be trace g the whole thing square minus trace of g square the whole by 2.
But 2 beta is not added.
Now, let me give you a more sophisticated derivation of this fact, which
This counting is same as saying if you give me an n cross n matrix,
Yeah.
it's symmetric, what are the number of them?
excellent, right? If you were just counting numbers, you would get this from there. If you just put g equals identity,
Yeah.
you'll get the right dimension. Nicely said, Shivansh. Okay, so that's correct. That's correct. If you just put, just set G equals identity, you'll get n square plus n divided by 2, which is the right number of symmetric matrices, and n square minus n divided by 2, which is the right number of antisymmetric, because that's n to n minus 1 by 2, or n to n plus 1 by 2. Exactly. Actually, let me, 1 minute since this has come up, I'll take like 10 minutes extra today, and we'll never talk about, in next lecture we will start with current algebra. Sorry we've gone on so much about Lie algebra, but since this has come up and it's, it's the fun part, it's the physics part, so let's, let me give you a derivation of this formula, which I find very nice. And I first read about in this lovely little book by Feynman, Lectures of Statistical Physics. It's a lovely little book, which nobody reads anymore. Let me give you this derivation. Let's say I want to do, I have n particles. So now what I'm going to do is to give you the character in this representation, where all n are symmetric. Okay, so I'm generalizing that answer. Okay? So, what do we get? Well, this was Feynman's idea. Feynman's idea was, look, imposing Bose statistics is simply summing over all permutations. So let me be more clear. Okay? Suppose I take the n particles and I permute them. Let's say that there is any particular permutation, I'll call it P. If I take any state psi, I act with P, sum over all P, and divide by n factorial. This imposes Bose statistics. I symmetrize, completely symmetrize. That's obvious. Okay? So, sum over all P of chi, sum over all P divided by n factorial is, take absolutely any state. Completely symmetrize it, you get a Bose symmetrized state, by definition. Okay? So, his idea was, okay, let me call this operation sum over P belong to permutation, belong to Pn, 1 by n factorial, and we know what P of chi, P of whatever, let me call that, let's think of this as an operator. Okay, so what we want to do, if we've got n particles, now I have given you that the single particle Hilbert space is Z of beta. That I've given you. What I want to do is count the n particle Hilbert space. Actually, you know of another way of doing it, which is to work state by state, not particle by particle. Right? Because each state can be occupied 1, 2, 3, up to n times. Anyway, but this is another way of doing it. It's useful because it makes contact with the Oberfolds. You'll see. Suppose I've given you that this thing is Z of beta. Now I want to compute the partition function of this symmetrized n particle state. Well, Feynman's idea was, look, let's say that the states were n, E1, E2 up to En. I'll just sum over them EI1, EI2, EIN. I'll just do the trace like this. I'll do trace unconstrainedly, but I'll put the projector P divided by n factorial, sum over all P. Sum over all P divided by n factorial, P of this, and then take trace. P is the permutation of that state. Clear? There will be n factorial such permutations. One of them is identity. One of them is some, some cycle length. Okay. This clear? This is what we have to do. Now, now what do you do? Well, notice that any particular permutation element is labeled by its cycle structure. Every permutation element is made up of n cycles. This you know, right? That every permutation is similarity equivalent to n cyclical rotation, to cyclical rotations, where you have m1 cycles of length 1, m2 cycles of length, let's call it, yeah, m2 cycles of length 2, up to mn cycles of length n. Is this familiar? Is this statement familiar? Every permutation element is similarity equivalent up to you take the first one guy, just cyclically, do nothing to it. Then the next two guys cycle, maybe 5 times do that, then 3 cycles and so on. Okay, okay. Now, if you had one of these permutation elements, okay, then how does it act on this guy? What it does is flip, let's say if it was a 2 cycle, it flips E1 and E2. If it was a 3 cycle, it flips E1 to E2, E2 to E3, E3 to E1. But after acting with the projector, you have to take inner product with this. Now, E1 and E2 are orthogonal states. So the only way you get something non-zero for on the ith cycle is if all E's were equal for those elements.
After permutation, it should be equal.
E1, let's say E1 has gone to E2. So what we want, let's say we're doing three guys and there's a 3 cycle. So we had E1, E2, E3. And this should be equal, now I'm permuting. So that's E2, E3, E1. Now this is non-zero only if this is equal to this. So E1 is equal to E2. But this is equal to this. So E2 is equal to E3. And this is equal to this. So they're all equal. Every energy on that cycle has to be the same. Clear? Okay. So let's say there are these equivalence classes of permutation elements. Equivalence classes are labeled by mi, the number of cycles of length I. Do you see that what you get is trace, so z of mi beta, sorry, z of, let's call it mn, n beta to the power mi. Divided by n factorial into something which is the number of elements in the permutation group with cycle structure, with this cycle structure. Do you see this? This is mi is a vector. You see, because everything on one cycle is equal, so all states have the same energy. So you're not summing over many different states. It's one state, but then you, if it's of length m, you weight by e to the power m beta e. That's this. Now if you've got many different cycles, and then there will be some n factorials also. Yeah, okay, that will all be accounted for here. The number of states with that cycle structure. Number of.
Is that the operation projection?
What?
The operation and 1 over t.
Yes.
The operator project. I mean, is the operator projection operator?
Yes, this is a projection.
I mean, like when it is paired, it becomes the same.
Yeah, let's take an example. Let's take two of them. It's 1 plus p by 2. Now let's square this. This is equal to 1 plus p plus p plus p square by 4. P square is 1. So this is equal to 1 plus p by 2. It's always a projection operator. Because all it's doing is projecting onto a subspace. The subspace of all completely symmetric wave functions. Once you've made yourself completely symmetric, then the operator does nothing. Right? Okay, great. And so this is your final answer. This final answer is clearly something to do with representation theory of the symmetric group. Because what you are asking is how many elements there are, in how many permutations there are with a particular cycle structure. Okay? And that thing can then be, in fact, I think that whole thing here, maybe I get some factor wrong. I'll probably get some factor wrong. Maybe the n factorial is still there. But it's related to the character of the permutation element labeled by Mi. This coefficient, when you work it out, I can't remember the factors. But the coefficient is proportional to the permutation element labeled by Mi. I'll just write down the final formula and then I'll explain what I mean by the permutation element. Is it related to some? Euler, I'm not very good with names. Let me just tell you what so it's sum over all permutations. Character of the permutation element labeled by Mi times chi of, now this is fundamental. Okay, chi of g to the power m, let me call it mn, because you want to distinguish my i's. G to the power mn to the power m. This character here is what? You see, the permutation group is itself a group. Okay? And oh no, it's probably character of identity. It's probably character of identity in the representation labeled by. I'll check this. It's probably character of identity in the representation labeled by Mn. That is, permutation elements are themselves a group. It's some character. Okay, I can't remember. It's some character in the of the permutation group. Whether it's character in which representation, you have to ask. Which representation? When I say character, which representation? Yeah. Okay. It's what is true is that representations of permutation group are also labeled by Young tableau. Okay. So these n's give you some labeling of the permutation group. Anyway, there's some simple thing here. If somebody can look this up, Schur character formula. This is a number. This is a number. And there may be some overall 1 by n factorial. I can't remember this, okay. I'll tell you next class exactly what this is. It's something to do with the representation. But you see that you get this structure with something that is very closely related to the theory of permutation group. Number of elements in, now I know. I'll tell you what. I'll tell you what. Sorry, it's this. It's character of representation Rn, Nm, but character in which representation? In the representation labeled by the Young tableau. So this formula works for any Young tableau. So suppose I want the character in the representation, I want character in representation Young tableau of G. Young tableau labels representation of SUN. But it also labels representations of the permutation group. Okay? So now you take character of Young tableau, of the representation of the permutation group labeled by the Young tableau, put the element of the permutation group being the element with this cycle structure. Well, the cycle structure determines only equivalence class, not elements. But all quantities that are equivalent have the same character. So that's good enough to determine this. Okay, and then you get this quantity. And there may be a 1 by n factorial here.
Sometimes it's product.
The sum is over all mn's. All mn's such that the total number of mn's equals the total number of boxes in the Young table. Is it Frobenius formula? Maybe. Maybe.
I see.
Okay, it's a beautiful thing. It relates these characters of SUN in an arbitrary representation to characters of SUN in the fundamental representation via the representation theory of the permutation. Okay, it's a beautiful, striking formula that's extremely useful.
The summing over these different elements of Mn,
Yes.
do all these elements have the same energy?
What do you mean by energy? Mn is just some
Sum over Ei times Mi.
Yeah, look here. The Ei times Mi was this Gn. See, the cycle structure is telling you about energies. Every element in one cycle, all these have the same energy. But in two different cycles have different energy.
But when you sum it over,
See, this is like product. Right? This is product over all n. Okay? So, 3 cycle to the power 4 if there are 4 3 cycles. That's this equal energy thing. Is this clear? Is the formula clear? I'm not sure of the number. We could even work that out actually. I think even the number is right because in the
The sum is equal to the character of this Young table.
we could check it for instance, that 2 box and get the number straight. I think this is right. Okay? So, this way of rewriting characters and arbitrary representations in terms of a character and a fundamental representation, often of huge value. Okay? And in the case of, it may be possible to do more generally, but in the case of SUN, it's very easy. It's given by this formula. Okay, I think we should stop unless there are questions or comments.
yeah, so there you said that character of in some representation should be some polynomial of place g to the power.
Yes.
Is this n specified? Will that depend on the group?
Yeah, it depends on the representation. If you've got a Young tableau whose total number of boxes is y, then the product, this product will only go such that n times mn sum over n is equal to y. Right? What you're doing is taking y particles in your Young tableau and imposing some symmetry structure. So the total number of g's that appear will be y. It's in y particle state with some symmetry structure. So this formula here, by the way, is the generalization away from Bose statistics. If we took only one row, that's Bose statistics. That we could easily do by hand, right? We just did it. But I've given you the formula not just for this completely symmetric or completely antisymmetric, which would be Fermi statistic, but for any representation. And this is imposing some mixed statistics on particles. And so it's not so easy to do. Is it the Frobenius formula, Unu? Is this called Frobenius? Frobenius formula. So this is called Frobenius formula. It's a beautiful thing.
So the right hand side only this character of the fundamental representation.
Only fundamental representation, but the group may be to some power.
Group, yeah, so group element have some power.
Yes. And the left-hand side is character in any representation.
Any representation.
And the coefficients are determined by representation theory of the symmetric, of the symmetric group.
And this is in Feynman's.
No, Feynman only did it for Bose statistics. Going away from Bose statistics is maybe, but physicists wouldn't naturally want to do.
So there is also a trace formula like this one representation to another representation.
What do you mean by that?
Some trace in some adjoint representation in terms of trace in some fundamental
That's this. Trace is character. That's what this is.
No, in the Polchinski's book, this SU anomaly cancellation, there is
Same thing, same thing, same thing. What you're doing is taking trace in some representation and rewriting it as trace in fundamental representation. Okay, often it's very simple, right? Adjoint in terms of fundamental is trace G times trace G bar minus 1. Right, because product of fundamentals. Okay, perhaps the last thing I can tell you is that product characters multiply when you tensor product states. This is some obvious statement. Trace, suppose you've got some tensor product space and you've got a tensor product operator. Then the trace of a tensor product operator in a tensor product space is product of traces. That's obvious. So characters multiply, characters are orthogonal. And so if you want to find out how I take the tensor product of some given representations, and I want to find out how many of some other representation, let's say representation R appears, there's a very easy way in principle, which is compute the character of each of the representations you're given. Take the product of all these characters. That is the same as the product of the characters of that is the same as the character in the tensor product. Then I want to pick out how many, in that tensor product, how many states of representation are over there. Well, I just multiply that by the character of representation R bar and integrate over hard measure. That will always be an integer, and that will be the number of particles, number of states in representation R when you take the tensor product. This is another very useful thing to know.
this way you can check that J1 plus J2.
You can do that, but okay, you can do more useful things also. Okay. Okay, let's stop. I'm sorry I've gone on so long.